We will do two class examples today for centrifugal pump. So one class example will be for geometrically similar pumps, and next class example will be for alteration in the same pump. So before starting working on those, let's do a very quick overview as we did in the class. So for geometrically similar pumps, we know that it will be like there will be at least two pumps. Okay. So one will be model and one will be, okay. So one will be model, two will be prototype, or you can name just the opposite way. One is prototype, two is model. Okay. And we will have these equations or set of equations, which is known as affinity law for Q or for discharge. Okay. Or discharge capacity, for pump head, and for power. So P here stands for power. Now there is a note I have added. For power, pumps have to be operated in the same efficiency. Okay, to be able to use this equation. If not, we have to calculate the power separately for the model and the prototype. Okay, so let's start working on class example 7. And I will discuss this set of equation for the alteration in the same pump before I start working on class example 8 again. Okay, so for class example 7, it says that a model pump of 7.5 inch diameter delivers 3 CFS water with 125 feet pump head. Speed and efficiency of the pump is 3600 RPM, which is rotation per minute, and 84% efficiency. Find the power input for the model. Then for a prototype pump of 125 feet, pump head of 80% efficiency, find the discharge speed and power input in horsepower for prototype, given that the size ratio of the prototype and model is 10. Centrifugal pump classification is given below. Find the type for model and prototype pump. Okay, so since we have multiple pumps here, one is model and one is prototype. So we know these are for geometrically similar pumps, and we will use those set of equations here. Now, let's write down all the given values that will help us to identify what are the given values and what we need to calculate. Okay, so since we have model and prototype, so what I will do, I will write down for model or prototype. Okay, so for model we have diameter, so I can use D1 or DM, it doesn't matter. So I'm just using DM, 7.54 inches. We have QM, which is 3 CFS. We have pump head, which is 125 feet, and the efficiency M, and the rotational speed M. So rotational speed M is 3600 RPM, and the efficiency is 84%. And we need to find the power input. Okay. So this one. And for prototype, we have I will just write down the parameters first, and then I will use the same sequence here. Oops, that should be P. dp. So let's see if we know any of these. We know the prototype pump of 125 feet. So this one is still 125 feet. We know the efficiency, which is 80%. We need to find discharge speed and the power input. Okay. Now we don't know the diameter for prototype, but if you look at one of the given information, it says that size ratio of the prototype and model. So for pump, size means the diameter of the propeller. That means size ratio of the prototype and the model. That means dp over dm is 10. Okay, and from that equation we can find the dp, which is dm 10, 7.4 into 10, so 74. Okay, so we need to find power for model, power for prototype. Additionally, we need to find discharge and the rotational speed for the prototype also. And then we need to find the type for model and prototype using this chart. Okay, let's start working on that. So the solution for model, let's start working on that one first. So it says that you need to find the power for the model. Now we didn't have any information about any power, but we had the information about the efficiency. So from that point we will start working on that. So efficiency of model, which is power output over power input, equals to 85%. So this one will be right. Now, since we are looking for power input or brake horsepower, okay, so what we will do, 84%, and oh, that is actually P input equals to, that is actually wrong. So it will be P input equals to P output over 84%. Okay. Now P input can't work with percentage, so I will just convert that into decimal. Now for P output, we already know the equation, which is gamma Q H, if you can remember that. Okay, so that's what we will use here, QH gamma, and everything is for model. Okay, now from that 0.84. So if I check the given value, gamma QM was 3 and H was 125. So we will just use that, and everything is in FPS unit. So gamma of water will be 62.4. So it will be 3, 125, 62.4. Okay. And if I do the calculation, it will be 27857. Okay, will be feet per second. Now, if we want to convert that into horsepower, what we will do, we will just divide that by 500 because the conversion factor is 1 horsepower equals to 500 pound per pound feet per second. Okay, so finally we will have 50.6 pound. What it's done, now we can work with the prototype part. So let's work on that. So for prototype, we need to find the discharge and the rotational speed. So let's do that. Rotational speed and what else we need to find? Discharge and rotational speed and the power, right? Okay, so I will just write down the equation for rotational speed in S and charge Q. Okay, and I'll write down the equation and then we'll see if we can find how we can find this stuff. Okay, so for discharge, the equation is QP over QM equals to NP over NM dP over dM to the whole cube. Now you can see that this from this equation, we need to know the rotational speed to get that discharge. And I made one mistake. That should be just N, not the NS. Okay. Now, for finding the discharge, since we need to find N, like rotational speed, so let's calculate that one first. Now, there is no direct equation for the rotational speed, but if we look at the set of that equation here, you'll see this is for discharge, this is for power, and this is for pump head. And we can actually use that pump head equation for the rotational speed because we have head and we also know the diameter. So this equation can give us the rotational speed. Okay, let's use this equation. Let's write down that. So the rotational speed is P HM in P in M square dP m square. Okay. So we know pump head for model and prototype is 125, 125. We know for model it's 3600 square, and for dP over dm is 10. Now, if we do the calculation, it will be 360 RPM. Okay, and now we can go here, QP over QM. So QP and QM is 3. That NP is here. So we can write down that 360 over 360 and 10 cube. And if we do the calculation, that QP will be 300. Right? Okay, so now we got to the rotational speed. we got the discharge. Now we need to find out the power output for the prototype. Now, if you look at the equation for power, you will see to use that equation, the efficiencies should be same in prototype and model, which is not the case here. So that's why we can't use that equation for calculating the power. So we will just calculate the power using the same way what we did for the model. So we will just use the regular efficiency equation and then we will find the power. So let's work on that. So for power, we know the efficiency of prototype is again power input, and it was 80%. Since we need to use that in decimal, I will just write down 8. Right? Now P input or brake horsepower equals to 0.8. Sorry, it will be power output over 0.8, and power output is gamma HQ again for prototype 0.8. Gamma is again 62.4, H is 125, and Q is this time it's 300.8. So we got 2925,000 lb feet per second. And if we want to convert that into horsepower, I will just divide that by 550 and the answer will be 5318 horsepower. Now, if you look at the model power, that was less than this 5318.18 horsepower. That's because that was the model and the prototype was in the actual one, which is bigger. So that's why that got this much higher power. Okay, now the last thing we need to check, we need to calculate we need to classify the prototype and the model power based on the specific speed. Okay, so that's what we will do here. So let's do that and before doing that, we need to check in which unit the table is given. So the table is given in capital NS, which is the dimensional specific speed. Here, if you look at here, so that's why we need to calculate the dimensional one. Okay, and let's check the range 500 to 335, 35 to 700, 7,500, and 7,500 to 1,500 radial mix and axial. Okay, let's check. Okay, so we will work on this part. Okay, so we need to calculate the specific speed. Speed model prototype, and the equation is in S in Q H 34, the same thing in S Q H 34. Now This NQH, they have some specific unit. We need to use that specific unit. So that N, it was in NPM, RPM, Q was in GPM, and H was in feet. So luckily, all the N we had it's in RPM already. So for the model, it was 3600, and for the Q, it was 3, and the H, it was 125, 3, 4. Now Q was in CFS, but we need to convert that 3 CFS into GPM. So we need to convert that. Now the conversion factor is 1 CFS equals to 448.8 GPM. That means we need to multiply this one like that, and we got 3533. Now here the speed was 360 and the Q was 300 multiplied by this one, and the H was, and if you do the calculation, you will get the same number, 3533. Now if you look at that, they have the same specific speed. That's because they are geometrically similar pump and they should have the same specific speed. For geometrically similar pump, similar pumps, NS for prototype equals to NS for model. And that's how you can replicate the results from, that's why you can replicate the results from model to prototype. So this is a very good checkpoint whether you did the correct calculation or not. Now, for classification purpose, if you look at the number, both of them are actually mixed flow pump. So you can write down that this one is not the fixed, mixed flow pump, and the same thing is here, mixed flow. So that's the class example about the geometrically similar pumps. If we know something about the model, how can we find the result from the prototype? So that was it. Now let's do the next class example, which is about the alteration in the same pump. Now alterations in the same pump means we are dealing with only one pump, and within that one pump, if we change something, like if we change the diameter of the propeller, how that will affect the discharge, or if we change the head, how that will affect the rotational speed, or vice versa. If we change the rotational speed, how that will change the head, or if we change the diameter, how that will change the power. So within one single pump, we are changing these, and we will check what is the effect of change on discharge head and power, and these relationships are known as performance characteristics. Okay, so our class example 8, it is all about this one, alterations in the same pump. Now from the questions, how we will know that it's alterations in the same pump or it's a geometrically similar pumps. So for geometrically similar pumps, you will always deal with more than one pump, and there should be some word like model, prototype, or small pump, big pump, something like that, and something about the replication. And for alterations in the same pump, it will be like a pumping, there will be just one pump, and within one pump, if you change diameter or rotational speed, uh, how that will affect the other parameters. The question statements will be like that. So here, a pump is tested at 1800 RPM, gives the following results: flow capacity 400, head 157, and power 190 horsepower. For A, obtain the performance of this pump at 1600 RPM. When they said performance of this pump at certain RPM, that means you need to evaluate the performance of Q, H, and P. So that's what we will do for A. We need to find the Q, H, and P. So let's work on that. So the relation between Q1 and Q2 or Q, it will be Q2 over Q1 and N2 over N1 and D2 over D1. And I didn't write down the given values, so I will just do that. So given values is N1 is given 1800 RPM, Q1 is 4000 GPM, H1 is 157 feet, and P1 is 190 horsepower. Now, I forgot if I mentioned that or not. It has to be without changing the efficiency. If there is no change in, like, you need to assume that there will be no change in efficiency. Only after that you can use this set of equations. Okay, now since we need to find Q2, Q1 is 4000, N2 is 16, so I will write down N2 1600 RPM, and N1 is 1800. Now D2 and D1, since it's within the same pump and they didn't say anything about changing the diameter, you can consider D1 equals to D2. Okay, I don't know the value at this point, but we can consider that they are equal. That means it will be just 1, and it will be 3555 GPM. Okay, so that is one thing. Now let's calculate the H and P. So for head and power, so for head, the equation is H2 over H1. We are still working on A, and the equation is N2 over N1 square, D2 over D1 square, and for the power, it's P2 over P1, N2 over N1 cube. If you look at the power of each one, you will see the first one was 1, for head it's 2, for power it's 3. So for head 2, head 1 was 157. It's actually 1600 over 1800 square and 1 square. And finally, it's 124.05 feet. For P2, P1 is 190 horsepower. Since you are working with like the same type of parameter on top and bottom, you can skip the conversion part. But if you want to do the conversion, you can do that. I'm skipping that part. That should be D2 over D1. Okay, and if you do the calculation, that should be 133.44 horsepower. Okay, now you can see instead of 157, we got 124. Instead of 190, we got 133, just by reducing the speed. Okay, now let's work with part B. Says that along with the speed, that means you already reduced the speed. The diameter of the impeller is reduced from 15 to 14, obtain the revised pump characteristics. That means now the N2 is already 1600 RPM. Now D2 is 14 inch and D1 is 15 inch. Okay, and all the other things, they are same. Okay, all the one part, like the N1 1800 RPM, Q1 is 4000 GPM, and the head one is 157 feet, and the P1 is 190 horsepower. Okay. Now again, we will do the same calculation here. So for discharge, Q2 equals to Q1 into N1 D2 D1, and Q1 is still 4000, N2 is 16 over 18, and now D2 is 14 and D1 is 15. Okay, if you do the calculation, you should get 3318 GPM. Okay, so if you look at the answer for the part A, the Q2 was 3555. Since you reduced the diameter, that is affecting the discharge capacity also. Now discharge head H2, and the equation was H1 into N1. That should be N1 D2 D1, and so H1 is 157, N2 is 16, 18, and D2 is 14 over 15. Then should get 108 feet. Again, previously the H2 was 124, so the head is decreasing also. And the last one is power. P2 is P1 into N1 cube P2 and P1 is 190, 1600, 1800, 14, 15 cube, and finally we are getting 108 horsepower. Previously it was 133. Okay, so that's it for geometrically similar pumps and alterations in the same pump class examples. Thank you.